Hello everyone, this is Professor Keen. In this lecture, I'll be talking about Proposition 4 or Theorem 4 of Book 3 of Newton's Principia. As I mentioned in my last lecture, this chapter is really the crown jewel of Newton's Principia, in which he's developing his universal law of gravitation. In this particular theorem, which is going to take a little bit of work to go through, what he's doing is he's arguing that the same force which causes the moon to orbit around the Earth is the force which causes terrestrial objects such as rocks or apples to fall when they are near the surface of the Earth. Before we go into this, let me just remind you of something that he said very early on in the Principia. This was back in his definitions, where he mentioned that if you have the Earth, let's say, right here, and we imagine, by the way, this is before he did any of his mathematics, this was simply kind of a foreshadowing of where he was going, and you consider a cannon placed on the top of a mountain, and the cannon shoots a ball. That ball will follow a parabolic trajectory. We know this from studying Galileo, and will hit the surface of the Earth. But if you shoot it a little bit farther, it will follow something that deviates from a parabola, but nonetheless, it will hit the surface of the Earth. And if you shoot it even farther, as it's falling toward the Earth is going to be curving away, and so it will go even farther. And if you shoot it horizontally with just the right speed, it will always be falling toward the Earth, but the Earth will always be curving away at just the right speed, and so it will go into orbit around the Earth. So in fact, an orbiting object around the Earth is simply an object that is falling toward the Earth and yet doesn't hit the Earth because it has enough forward momentum or forward motion so that as it's falling, it never quite hits the Earth. So here we see the kind of the underpinnings of Galileo's theory of orbital motion. It's a combination of the principle of inertia. An object in motion tends to stay in motion in a straight line unless a force acts on it. And if a force acts on it, it will either speed it up or slow it down or deflect its motion in some way. So you have a combination of the principle of inertia. The ball wants to go in a straight line, but there's also a centripetal force, a force pulling it in, deflecting it from its straight line trajectory and causing it to go in an orbit. So that's really the philosophy or the idea behind this. And what he's doing largely now in this chapter is saying what kind of force it must be that is holding this cannonball in its orbit. What is the nature of this centripetal force? Okay, so having said that, let's go through his this paragraph that comes right after Proposition 4, Theorem 4. Okay, so here's what he does. I'm going to number these as I go through them. First of all, what Newton does is he recognizes that the Earth's, the radius of the moon's orbit is, I'll call it capital R, is 60 times the radius of the Earth. Okay, so if we were to think about the Earth, so this is, ignore this picture now, let's do a different picture. Here's the Earth right here, and let's draw a line right here. And let's suppose that this right there, that's the radius of the Earth itself. And then we put the moon out here, and the moon is orbiting around the Earth, and it has some orbital radius, and that orbital radius, r, is 60 times the Earth's radius. In claiming this, Newton appeals to several different measurements of the distance of the moon's orbit dating back to ancient times. This was actually pretty well known even by the ancient Greeks. But he provides more recent measurements, even going up to, I think, the work of Tycho Brahe and others who had very precise measurements. And he says they all kind of converge on this value of 60 times the Earth's radius. So if you know the size of the moon is orbiting about 60 times farther away from the center of the Earth than the surface of the Earth is. Okay, that's the first thing that he points out. The second thing he points out is the time of the moon's orbit. So the moon orbits Earth with a period, an orbital period of t equals, he gives us 27 days, 0.7 hours, and 27 days, 7 hours, and 43 minutes. Okay, that is the time it takes for the moon to go around the Earth one time. Okay, you might, just so you're not confused, sometimes the lunar month is reported in different ways. So the time it takes for the moon to go all the way around the Earth compared to the other stars, that is this time right here, 27 days. If you're looking at the time it takes to go through all of its phases from new moon back to new moon, that's about 29.5 days. And there's a subtle difference between those two, but the relevant one, I'll just say for our cases, is this what's called the sidereal month as opposed to the synodic month. So this is the sidereal month for the connoisseurs among you who might know the difference between those two. The sidereal month is having to do with sideres, the Latin word for stars. So you measure the motion of the moon compared to the distant stars as opposed to the sun. Okay. All right, so that's the second point, the time it takes the moon to go around the Earth. By the way, if we know the radius of the orbit, you can figure out the distance it goes, because the circumference is the distance, that's 2 pi times the radius. And if you know the time it takes, if you know the circumference and the time, you could figure out the speed that the moon is moving in miles per hour or meters per second or whatever you wanted to. And you could figure out how far it moves in, let's say, 1 day, how many miles it moves in 1 day as it goes around the Earth, or 1 minute or 1 second or whatever. And so that's just a heads up where we're going to go with this. Okay, number 3, he mentions that the circumference of the Earth is, I'm going to round off, 123. Well, he says 123,249,600. I'm just going to round off 123 million Paris feet. So there were different standards at this time. We didn't have the international system of units, so each country had its own units that they were using. About 123 million Paris feet. By the way, why does he say this? Because if you know the circumference of the Earth, you can work backwards, find the radius of the Earth. And if the moon orbits at a distance 60 times greater than the Earth's radius, then you know what the radius of the moon's orbit is. So that's the reason he brings that up here. Number 4. Okay, now here's where we get a little bit more technical. All right, so what he's going to do here is he says, let's assume that the force acting on the moon, which holds it in orbit, this is the centripetal force that must be acting on it. The centripetal force is an inverse square force. That is, the centripetal force is proportional to 1 over the distance from the center of the Earth out to the moon squared. Why should we assume this? Well, it's not really an assumption. He gave a plausible argument that this is the case in the very previous proposition, proposition 3 or theorem 3 in book 3. That's the one we went through in my last lecture. Okay, so very nearly the force acting on it goes as 1 over r squared. Now here's the question that he's going to ask is, how far would the moon fall in 1 minute if we were to somehow stop its orbit and let it, under the presence of this force, simply move inward? How far would the moon fall due to this force pulling on it, pulling it toward the Earth, if its orbit were suddenly halted? Right? So imagine that the moon's going around and suddenly God puts his hand in here, stops it, but he doesn't take away the force, its centripetal force. And so the moon, as a result of that inward force, starts falling. How far would it fall in the course of 1 minute? How would it fall due to this force pulling towards it, or suddenly halted? And I want to know that in 1 minute, he says, how far would it fall in 1 minute? Well, he has already figured this out. So he's going to say, well, let's use back in book 1, proposition 4, corollary 9 of book 1. This is why we did all this previously. What we did back then is we said, well, if you have something that is moving in an orbit, and by the way, we did a lab on this too. And let me draw a few lines here. And this object we're orbiting, in, let's say, a time of 1 minute, it's going to go through some arc length. And if instead it felt the same force and you let it descend with the same force for the same time interval, let's call that distance it descends x. This would be the arc length through which it would move if it was orbiting, and this was the diameter of the orbit. Remember, there was a relationship between that distance of fall, that arc, and that diameter, namely that the distance of fall, the arc is a mean proportion of x and d. So x is to the arc length as the arc length is to the diameter. That was proposition 4, corollary 9 in book 1. So why is this relevant here? Well, because he says there's this centripetal force acting on the moon. Normally it would move through this arc length let me redraw this so I don't get too confusing in my drawings. Well, actually, I'll just use this one right here. Normally, the moon would go through this arc in 1 minute, but instead, if we stop it and let it fall for 1 minute, how far would it go? Well, we can figure that out. How can we figure it out? Well, like I said before, if we know the circumference of its orbit, we know the time of orbit, we can figure out its speed, we can figure out just how far it goes in 1 minute. If we know the diameter of its orbit, which we do, we could plug in its arc length, the diameter, and figure out what x is. And he finds that the distance it falls, x, would be about 15 1/12 feet, or about 15 feet 1 inch. So that is the distance the moon would fall in 1 minute if the orbit stopped, but the centripetal force were still acting on it. Okay? Good so far? All right. Now, let's go on to his point 6. So you see here what he's doing here is he's kind of relating falling object to orbiting object. Now, let's suppose that instead of the moon being way out here orbiting, let's consider the moon were orbiting really close to the surface of the Earth. So suppose the moon was located or orbiting right near Earth's surface. I know this is a hypothetical scenario, but let's consider this. Instead of at a distance of 60 Earth radii away, it was at a distance of 1 Earth radius away, right? So we've got this new imaginary moon that's orbiting right here at the surface of the Earth and kind of going around right at the radius of the Earth. What would we anticipate would be the answers to these kinds of questions we've been asking? Well, we can actually figure that out, because if, as we suggested, if the centripetal force is proportional to 1 over r squared, then as it's closer, it would be 60 times closer. So the force would be 60 squared times stronger. So then the force acting on the moon would be stronger by 60 squared times. After all, a 1 over r squared force means that if you replace the radius by 1/60th of the radius, 1/60th squared in the denominator makes a 60 squared in the numerator, which means that the force is 60 times greater. 60 squared times stronger. All right, so the new centripetal force, F prime, we'll call it the new one for this new planet, would be 60 squared times whatever the old centripetal force was that was holding it in orbit way out here. Now, furthermore, if the new centripetal force was 60 squared times bigger than the old centripetal force, then by his second law, Newton's second law, which is F equals ma, so if this is the case, then by Newton's second law, the acceleration would be 60 squared times bigger. That is, the new acceleration that it feels would be 60 squared times the old acceleration, right? And continuing this line of reasoning, if it's feeling 60 squared times bigger acceleration, then we can figure out how far it would fall in that same time period. If the distance it falls is 1/2 a times the time squared, then because this acceleration is going to be 60 squared times bigger, because this will be our new acceleration, then the distance, the new distance it falls, would be 60 squared times the old distance that it falls. That's because the force is stronger, the acceleration is stronger, and in 1 minute it's going to fall 60 squared or 3,600 times farther. Okay? But now, suppose, this is point 7, suppose we consider not how far it falls in 1 minute, not 1 minute of fall, but 1 second of fall. How far would it fall in just 1 second? Well, going back to this formula right here, distance is 1/2 at squared. If the acceleration is 60 squared times bigger, but the time, 1 second, is 1/60th of a minute, that's 1 over 60 squared. So if the new acceleration is 60 squared times the old acceleration, and the new time we're considering is 1/60th of the old time, then the distance, the new distance that it falls, I guess this would be a new distance too, would be 1/2. The 60 squareds would cancel out. So you have 60 squared, your old acceleration. Now, let me just go back. If you have 60 squared times bigger acceleration and 1/60th squared times the time, then the new distance, x prime, is the distance fallen in 1 second, is going to be just 15 and 1/12 feet. Because after all, when it was out here with the weak force, the small acceleration, in 1 minute it fell 15 and 1/12 feet. In here, with a much bigger force, a much bigger acceleration, but considering a much smaller time, the new distance it falls is 15 and 1/12 feet. Does that make sense so far? Okay, so what he's done is he's said, we can figure out how far, if this moon, this little moon near the surface of the Earth, if it was feeling this 1/r² kind of force, we could figure out how far it falls in 1 second. And here is the crux of the argument. He says you can actually measure how far things fall when you drop them in 1 second near the surface of the Earth. And the fact is, objects that on Earth's surface, or near Earth's surface, fall about 15 and 1/12 feet in 1 second. This is a stunning observation. He's saying that this force that's holding the moon in its orbit, if it's a 1/r² force, if you consider what would happen if you held the moon near the surface of the Earth and dropped it and it was subjected to that same force, it would fall the exact same distance that typical objects fall when they're at the surface of the Earth. Let me stop there and I'll finish up this lecture next time.